need the ring. The ring.
Yes, Eugenio Omodeo will do it, but give me the please, Eugenio, give me the title.
Okay. In fact,
speak of one equation to all that one.
so I'm going back to a paper, an old paper, almost 50 years old paper by Martin Davis named One Equation to Rule Them All. And a former student of mine, Luca Vallato, who is here in this audience, asked me, was this title inspired by Tolkien's novel, The Lord of the Rings? And Martin Davis said, yes, this was the case, and I had some political argument with the Rand Corporation, and this is where the title comes from. In outline, my talk will be about classical issues in the study of Hilbert's tenth, namely existentially definable, in particular Diophantine sets, relations of exponential growth, Martin Davis, Martin Davis quaternary part equation. This is what the paper of 1968 was about. So in that paper, Martin Davis showed that if one could prove that this equation has only one solution, then Hilbert's tenth problem would be solved in the negative sense. Now, then we will examine integers expressible in the form x squared plus 3y squared, and I propose a novel quaternary part equation which seems to do the same job, seems to be able to do the same job as Martin Davis' original quaternary quartic. And then we will address the issue: is the exponential growth this exponential growth relation Diophantine? So what do I mean by this relation? I mean the set of all pairs in which this is the solution to this pair equation with A equals 2. This is why you see a 2 here. So this is the solution which occupies this position in increasing order of the solutions. So is this set of pairs of exponential growth? If so, this will be the case if and only if this has not if and only if this quaternary particle equation has a finite number of solutions. Now let's go to the classical notion. A relation is said to be existentially definable in terms of some relation J like Julia Robinson, if and only if the n tuples which belong to R are precisely the ones for which there exist x's satisfying this formula phi, where formula only involves the shown variables subdivided into parameters and unknowns, positive integer constants, addition, multiplication, and some logical connectives which do not include the negation nor universal quantification. And of course also J is allowed to enter into the formation of phi. And it may seem an oversight that I did not mention subtraction, but this might collide badly with J, because J typically is exponentiation. So the power of a negative, so if a negative number appears in the exponent, it may cause headaches. So when J is absent, R is also called Diophantine. This is not the official definition of Diophantine, of a Diophantine n-dimensional set, but it's easy to see that the two are equivalent. Now, so if we want, we can extend the language in which phi is written by any relation which is Diophantine. So, for instance, these two are existential definitions of the singleton of 0. So, in my former slide, 0 was not allowed because we have only positive integer constants. But once I have an existential Diophantine definition of 0 like this one, then I'm allowed to add it to the language. And much in the same manner, I can add greater than, less than, not divides, is a square number, because these are easily expressed in the language of Diophantine relations. Now, these are toy examples, but there is an example which is not so toy, which has to do with listable sets, also known as recursively enumerable sets. Intuitively speaking, such a set is one whose elements can be generated exhaustively by an algorithmic, perhaps non-terminating procedure. Perhaps non-terminating has to do with the fact that typically a listable set is infinite. And there is an important result of 1961, roughly, published in 1961, which says that each listable set is existentially definable in terms of exponentiation. And this was discovered by Davis, Patram, and Robinson, so it's known as the DPR theorem. And related to existential definitions, we have another notion. An existential definition, such as the one we have seen before, is said to be a single fold if there are two solutions corresponding to the same vector of A's. So take the actual parameters a1 through an. Either there is no solution to this formula, or there is exactly one. So an improvement to DPR came in 1974 with a paper by Yuri Matasiewicz showing that each listable set admits, showing that every listable set admits an existential single-fold definition in terms of exponentiation. In a way, we could call it the small DPRM theorem, not an important one which led to, and in fact, later than posterior to the one which showed the unsolvability of Hilbert's stem. Now let's talk quickly about the dyadic relations of exponential growth. So from now on, J will designate a relation which satisfies these two properties. V does not grow too fast with respect to U, but nevertheless its upper bound is very big. And for every L, there is at least one pair in which satisfies J, and such that U to the L is smaller than B. So these are also known as Julia Robinson's predicates, because they were studied in a paper published by her in 1952. And there is an example of historical importance of a dyadic relation which meets these two properties, which is the set of pairs U, F sub 2U, where this is the progression of Fibonacci numbers. In fact, this is the one. This is the relation which Yuri Matesiewicz exploited in his paper in 1970. So the context is the following. According to Julia Robinson, if you find so in terms of any j of exponential growth, you can express exponentiation. So this is a general scheme in which you can plug in any exponential growth relation, and in every case it will give you a specification of that ternary relation. And once you have that, you can thanks to the DPR theorem, you have the possibility to express every listable relation in terms of I. But suppose now you can show that I is Diophantine, then every listable set becomes automatically Diophantine. And this is precisely what Yuri did in his 1970s, in his paper of 1970. He showed that the progression of the relation associated to the Fibonacci progression was Diophantine. This is essentially the original scheme due to Julia Robinson. You have here a special exceptional treatment for the case when n is 0 or b is 1, in which case c must be 1. This is also a special case in which b is 0 and n is non-zero, then c has to be 0. And this is the really intriguing part of the reduction, in which Julia Robinson did not have this a predicate of this form, but a relation in two variables which enjoy the properties similar to this one. This q here is a polynomial which a Diophantine polynomial, namely a polynomial in integer coefficients, which will equal a square number only if y exceeds x to the x, and which assigns at least one image to every x. And such a polynomial can be found in a paper jointly published by Yuri and Julia Robinson in 1975.
And what do you know by square and black dot?
So this is just an existentially quantified variable which occurs only once. So I can leave it anonymous. I could also write here, say k, and add a k in the list of existential variables. So its status is similar to this variable, which is also an implicitly existentially quantified variable. So here, say, I could add here an h and replace this by h squared, h to the square.
Okay, so it's a variable which is a square. Okay.
Yes.
And dot is not necessary.
It's not necessarily square. So these are the well-known Yuri's equations for the Fibonacci relation. And this is once, so these come from a presentation which Martin Davis gave in Italy some time ago, and I once asked him, are these the original equations by the original equations and said, yes, they are the ones which I first saw in notes taken by John McCarthy from a lecture in Novosibirsk in, I think, either in January 1970, I think. Now, there is, before this result, Martin took into account these two sequences. These are the two sequences associated with the Pell equation x squared minus 7y squared equals 1. And each number in this progression is 16 times the one which precedes minus the one which comes even before. So, to say it better, x sub I plus 2 equals 16, x sub I plus 1 minus x sub I. And there is a similar double recurrence defining the y's. And through the study of integers expressible in the form u squared plus 7v squared, there is proofs that the exponential growth relation, this exponential growth relation is Diophantine if this equation has no solution in n except the trivial one, u and r equal 1 and v and r equals 0. And so this is the 2/11 solution of this Pell equation, and it's easy to see that this is an exponential growth relation. But the issue is, can we specify it by merely Diophantine means? And unfortunately, Martin's approach was at first sight wrong, because today at least 50 solutions to his quaternary particle are known. 2 were discovered I think in the early 70s, and many more in the 90s. And but luckily, I believe Julia Robinson, but I'm not sure. This is what Shanks and I can't remember the other name, Shanks and whatever. What they attribute this discovery to Julia Robinson. It's rather simple, but it was not easy for me to rediscover it. Julia Robinson shows that Martin-Davis equation nevertheless does its job, provided its overall number of solutions is finite. So this is good news, and an even better news is that as Davis, Matiasiewicz and Robinson wrote in 1976, it can be shown that a single-fold Diophantine representation of exponentiation can be constructed if the equation, the quaternary particle equation of Martin-Davis, has only a finite number of solutions. So this is the added value, and this in a way would be a combination, a combination of the virtues of the small Davis, Putnam, Robinson, Matiasiewicz theorem, and of the official DPRM theorem. However, these two authors conjecture that the equation by Martin-Davis has infinitely many solutions in integers. And to make their conjecture even more intriguing, they suspect that this is not decidable. I mean, I think what they mean by this is that although the number of solutions in integers is infinite, perhaps this is neither provable nor refutable in Peano's arithmetic. So this is a bad news if we believe to their conjecture. In a way, it's even though they easily found 50 solutions, they do not claim that this is evidence for their conjecture. They offer some arguments which may or may not be convincing. I'm not expert enough to judge. But anyway, upon Martin Davis' suggestion, we looked for another candidate to the role of one equation to rule them all. When I say we, I mean myself and my co-author, Domenico Cantone from the University of Catania, who was mentioned in the first slide, which has disappeared at some point. We started with a different Peltz equation, this one, which is an instance of the very appealing form x squared minus 8a squared minus 1 y squared equals 1. So this is the kind of Pell equation which has, on which most of the exercises on Hilbert strength were done starting in the 50s. And we focused on integers expressible in the form u squared plus 3u squared. And first of all, we had to treat the prime numbers of this form. Prime numbers of this form caught the curiosity of Fermat and Euler, and actually Fermat claimed that these numbers, the prime numbers of this form, are precisely the numbers which are not congruent to 2 modulo 3. So those are 3, which is the only one of its kind, and all numbers congruent to 1 modulo 3. And this fact was proved by Leonhard Euler in 1772. Fermat also claimed that he had a proof, but this was not left to us. And now let's call Poisson prime. So the fact that this is nowadays a fact which is easily found in books. For instance, there is a book by Cox published in 2013 whose title is x squared, primes of the form x squared plus ny squared. So when I first attempted to prove this, which I had also found in a way experimentally, just because I suspected it, some similarity between 3 and 7, which was suggested by reading Martin's paper. When I just asked Google primes of the form, I just found this book, and I could download the book and find a full demonstration. Now, in Martin Davis terminology, we can call Poisson prime any prime which is not representable in the form. So one which is representable which is not representable in that form. One which is which belongs to this congruence class. We found that the positive integers of the set form, I mean of this form, are precisely the ones such that no Poisson prime divides m to an odd power. So in a way, it is like as if when a Poisson prime divides an integer, a positive integer, by an odd power, it infects it and makes it no longer representable. Even if another Poisson prime divides m to an odd power, then a number cannot be represented. So to a number theorist, to a competent number theorist, this sounds as something rather simple. I asked a colleague in Udine called Pietro Corvaro, who said, yes, The reason of this fact is that this ring, which consists of the integers in the third cyclotomic field, is a unique factorization ring. And my author and I simply bypassed this suggestion and found our own proof. It's not very difficult, but you have to become familiar with Legendre symbols, and after all, once you see, it's not very difficult proof. Now, consider the increasing sequence of the y's which solve this Pell equation. So this is x squared hidden in this box. Then the numbers of this form, so the ones whose, so the components of this sequence whose subscript is a power of 2, which are representable in the form, are precisely the ones which are odd, which have an odd exponent, sorry. And now let's move on to a number which whose subscript is not a power of 2, but it has also which has also an odd divisor. So if this is representable in the form u squared plus 3b squared, then y sub this is also so representable. And it turns out that these two numbers, if this is representable in this form, then y sub h is also I'm not sure whether it's, no, it's y sub this, which is representable in that form. And it turns out that also these two, which are relatively prime numbers, are representable in that form. And from the two preceding remarks, it follows that if n is representable for some n greater than 0, not a power of 2, then this system has a solution in n for which y is different from 0. So, what are these? These are x to the h, y to the h. They must solve this Pell equation. This is representable. This is also representable. And if h is greater than 0, then this will be different from 0. Then, from this system of equations, by some algebraic folding, which is not particularly profound, we can get this quaternary quartic. So this is exactly the same mechanics which was used by Martin Davis in his 1968 paper. The only difference is that here he had a 7 instead of 3, and it's not so clear to me why. He could not explain why he started with 7 instead of with 3. Why did he skip over 3? And in fact, when I started this study upon suggestion of Martin Davis, because when I wrote to him that I wanted to submit something to the conference in honor of Yuri Matesiewicz, he took a few days to think and then suggested this topic. And he suggested, why don't you try to put here an 11? But 11 didn't work. 11 didn't work because there was no easy connection between representability and congruence classes. And so the analog of a Poisson number could not be found. Now the issue is we have a new interesting set of pairs of exponential growth. In this case, instead of having two, I don't remember what was in the original, in the case of Martin's original paper, now we have to plug in here the 2 times L plus 1th component of the sequence of y's. This view here is the largest power of 2 which divides this number. And the question is this a Diophantine set? So let's call it GPTM, the greatest power of 2 which divides M. So we can express that A exceeds or equals the GPT of B. We can state this in the form there exist x and y such that B equals 2x, x plus 1 times y, and A is greater than or equal y. So this is, even though this talks about the powers of 2, this is a Diophantine rendering of this relation. And the issue which I raised in the preceding slide, namely, is this relation Diophantine, reduces to the question, is this set Diophantine? And if this is the case, then we have a relation of exponential growth which is Diophantine and which can do the same job as the relation associated with the Fibonacci sequence. Now, let's consider this. The following are necessary and sufficient conditions in order that W belongs to this set. W has to be greater than 0 because all y's except y0 are greater than 0. This has to be W has to be a solution to our Petz equation, x squared minus 3y squared equals 1. And W must be expressible in this form because we have a theorem saying that the numbers in which so the numbers y sub 2 to the m representable in this form are precisely the ones in which m is not number. And then just in case the quaternary particle of the preceding of the preceding slide, and this one has more than one solution. Just in case, in that case, we also need this condition. Oops. That no number of this form can divide W, where R, S, U, and V are a solution, a non-trivial solution to this equation. So, if the equation has only one solution, we don't need this. If it has more than one solution, we don't need this. But in any case, even though this is not explicit, this shows that the predicate is Diophantine, because it's Diophantine if the number of non-trivial solutions is finite. Because if the number of non-trivial solutions is finite, then we have a conjunction, a finite conjunction of conditions of this form, and these are Diophantine. So this results in a Diophantine specification if the number of solutions to this novel quaternary part is finite. So we are a competitor to the old quaternary partic. Is it true that this has only a finite number of solutions? I think this is where the real game begins starts. A friend of mine, Alberto Polcriti, devoted a lot of efforts in this, but didn't make. So we have an Italian proverb that says he did not pull the spider out of the hole. So he made a lot of efforts, but without any success. And another question, which is a question for myself, but which probably, by analogy, I suppose will have a satisfactory answer. If the number of solutions to this novel quaternary partic equation is finite, is then true that exponentiation has a single-fold Diophantine representation? So by analogy with the case of 7, which was addressed by the trio Davis, Robinson, Matiasiewicz in 1976. By analogy, I guess so, but in fact I'm asking, in these days I'm asking viewers 2 minutes, okay, but I'm done because I'm just going to, what remains to be discussed is what is the future work. Determine whether the novel quaternary partic has finitely many solutions. If so, supply a concrete Diophantine definition of this. And because the one we have seen is not a concrete Diophantine representation, it's just a feasibility study. Unless we know all solutions, we cannot specify it. Independent of that, how does one get the single-foldedness of exponentiation? And are there any other competitor for the role of one equation to rule them all? Apparently, the only competitors are the ones which ensure that the integers of Q extended with the square root of minus n form a unique factorization ring. So there are 9 candidates, of which it seems to me that only 3 and 7 survive. Thank you for your attention. And here there is some bibliography. I have a draft paper of the text of this work here. Whoever is interested can get it a PDF from me. And part of the motivation for this talk comes from indications that I found in a paper by Yuri, included in this anthology of essays on Martin Davis' history. Thank you for your attention.
Have you any questions or remarks? Yes, Julien?
Why do people think that the fact that there is an infinite number of solutions for this equation is not provable or refutable?
Why do they think that the infinite number?
Why it is not provable or refutable in the PA?
They don't argue. They say simply this might be the case. We've become aware of this possibility, and if this happens, this becomes a really intriguing question. So that single, the existence of a finite number of an infinite number of solutions might be as hard. It's a very simple statement, but which might be as hard as the consistency of arithmetic.
Yes, Maxime?
And what is your own belief? Are there infinitely many solutions or finitely many?
To some extent, I subscribe the expectation of my colleague Alberto Policriti, who thinks that either the solution is one or there are infinitely one, and mainly because a Pet's equation enters too heavily into the construction of that polynomial. So either the two extra constraints really are able to force the solution to be one, or probably there are, so he also suspects that there are infinitely many.
Okay. And maybe one more comment. So you said that in principle, while we try and look on other equations related to quadratic fields with class number 1, maybe instead of looking on the sum of squares like x squared plus 3y squared, can take some quadratic form of the corresponding discriminant, which is not the sum of squares, but there are forms that have nice properties with, in the sense that representability is expressible. Representability of primes is expressible by congruences modulo the discriminant.
This might be a suggestion, but my policy is, in this case, like in the case of an article which I present, which Luca Vallanta presented at the former JAF conference in New York. My policy is reach a goal and then get some real true number theorists involved. And in fact, the list of authors of this work are temporarily two, but I hope that then I will have Pietro Corvai involved. You may know him, and he's a genuine number theorist. I'm relatively not enough expert to answer your question.
Thanks again.